Hey there, class. We're here today. We're going to look at example 2. This is from our circular notes. And so basically this is a classic problem. Car we have going around a corner. It's on a level road. So this is important. Level road simply means that it's not banked, so you don't have some kind of car going, on a banked corner like this. That means that basically we don't need to worry about components on this one. If there was any kind of banked corner, kind of like we have here, we would need to deal with components. So no components when we see that it's on a level road. We have a maximum frictional force the road can exert on the tires is that. Now, we'll get to this when we talk about the understand part, but this is not slowing the car down. And again, we'll get to that in just a moment. So what we want to know here is what is the maximum speed? So this is our find. And what they can go around this corner. All right, so let's scroll down here and let's see what we understand. So one thing to note here, the view that I'm taking for my free body diagram is what we call the chase car view. So in other words, it's almost as if we were following behind the car. We're kind of on the ground level, we're looking at the car kind of from behind it. So you're not going to actually see the curve that this is on, but this would be the radius here. The 200-meter radius. So let's finish these forces. We of course have the downwards force, the force of gravity. That's kind of an obvious one. We also have the road pushing upwards on the car. This of course is what we would refer to as the normal force. We also have, and this is where conceptually this can be a little bit tricky, but once you understand what's going on here, this should make sense. This is actually the road pushing on as well. Towards the middle, and this is actually the frictional force that we are talking about over here. This is that 4,000 Newton frictional force. And again, the reason for this is if there were no friction, okay, if there were this friction that kind of holds the car in, this car would travel in a straight line path. So again, if you looked at the kind of a top view of what's going on, this path that's traveling on is actually curved. But again, an object doesn't like to travel in paths. According to Newton's first law, it should travel in a straight line. So again, not traveling on a curved path, not traveling on the curved path here, but it would travel in a straight line. But the friction, okay, the friction is going to kind of keep it pulled in towards the middle. And this is what's going to provide the centripetal acceleration. So the centripetal acceleration, again, is an acceleration that is directed towards the middle of the circle, and sometimes we again refer to this as a radial, radial acceleration, because again it's along the radius of our circle. So our goal here again is to find the velocity. From this vantage point, we cannot actually see the vector. So one way we can draw this, and we can do a video for this later, but basically you're looking at the vector from behind. That actually looks like an X. If it was coming towards us, we'd draw it as a dot. And again, that's for another video at some other point in time. All right, so the maximum speed that's going to occur is going to occur whenever this is at a maximum as well. So the force of friction will be at a maximum. So we'll use the 4,000 in our work. All right, let's come up with a strategy. Okay, so pretty much what this comes down to is we can think about this. We know that the velocity that we're going to try to find is involved with acceleration. So acceleration is something that probably we're going to do something with. Well, that's in Newton's second law. So the sum of forces equals mass times acceleration. In this case, there is only one force that's causing the acceleration. Of course, the normal force up and the gravity force down cancel out. So we're pretty much left with the force of friction, which is going to cause the mass, that's the car, it's going to cause it to accelerate. Now keep in mind, we are trying to find velocity. So I'm going to make a substitution. The acceleration we're talking about here really is a centripetal acceleration, which is v squared overall. So I'm going to substitute, okay? I'm going to substitute that in, and we're going to get the force of friction equals mass times velocity squared over the radius. Doing my mental checklist, I know that I have the force of friction. I know that I have the mass. I believe I have the radius, and I believe this right here, this is the goal. This is what I'm actually trying to find. So basically now it's just a matter of basically solving this, solve for the V. I'm going to do that behind the scenes and come back when I have that done. Okay, so behind the scenes, I was able to isolate the V algebraically, and I end up with this equation right here. So I'm going to go ahead and we're going to substitute in our numbers in my implementation. And once again, I'll do this behind the scenes and do the calculation, and we'll catch up on the other side. So behind the scenes, what I did here was I substituted my numbers in right here into this equation. So the 200 meters is the radius, the force is 4,000 newtons, and my mass was 2,000 kilograms. Conveniently enough for us, basically we end up inside here, we end up with a 400 inside the square root symbol, and of course that's a perfect square. Turns out that the speed that we're going to end up calculating is speed of 20 meters per second. And so that is the maximum speed that our car can go around without slipping.